In the last video, we managed to convert the mathematical definition of a straight line into a set of pixels on the empty canvas. Upon closer inspection, we noticed the lines were too dark, jagged, and thick, and therefore did not look like strings of threads at all. So in this video, we shall fix that by altering the model a little and also by implementing that model using a different method. In translating the ideal model of the line into a set of pixels on the canvas, we took a decision to make those pixels over which the lines passed black. This idea is a mistake because it does not discriminate between pixels over which a longer segment of the line passes against those pixels over which very little of the line passes. This scheme essentially makes lines with different slopes have different thicknesses and different levels of jaggedness. So obviously, pixels which harbor greater line lengths should be darker in comparison to those which have very little of the line passing over them. That is the more reasonable assumption. So let us go ahead and implement that. To do that, we could go to each unit of length on the x-axis, find the pixels over which the line passes, and then calculate the length of the segment on each pixel. Based on that number, we could then set the darkness of the pixel. That's a perfectly valid approach. But I am going to do something different, which gives me more control over how I'm going to implement the said approach and also makes the model easy to tune later. In my approach, I am not going to calculate the length of the line over each pixel, but do something else that gives a rough measure of the same thing. That is how much of the line passes over the pixel. What I'm going to do is set the darkness of the pixel based on how far the pixel is from the line. Or to be more precise, depending on the perpendicular distance of the pixel from the line. This approach is, in my opinion, more elegant than all previous approaches and makes things much easier to manage and control, as you shall see. Now the question is, how do we calculate the above mentioned perpendicular distance? If we want to find the distance between the point A comma B and the line y is equal to mx plus c, let us first draw a perpendicular from the point to the line and assume they meet at P comma Q. If d is the distance between the point and the line, then from the Pythagoras theorem, we have d is equal to square root of q minus b squared plus p minus a squared. Now this perpendicular line would also have an equation of the form y is equal to m prime x plus c prime, and therefore we could say m prime, which is its slope, is the ratio of the rise of the line over its run. Squaring this equation on both sides, rearranging a little and adding p minus a squared on both sides, we get the left hand side of the equation to be equal to d squared. Therefore, the distance d is equal to the absolute value of p minus a times square root of 1 plus m prime squared. Since both lines meet at p comma q, we could equate q on both line equations. Doing so, and after some rearrangement, we get p as this ratio. Now the question is, what are m prime and c prime? To find m prime, let us take two perpendicular lines and make two triangles from them like you see here. Since triangles ABD and ADC are similar, we get DB over AD equals DA over CD. But DB over AD is the slope of the first line and DA over CD is the reciprocal of the slope of the second line. So these slopes are reciprocals, and because the second line is sloping down while the first one is sloping up, both would naturally have opposite signs. Therefore, the slopes of perpendicular lines are negative reciprocals of one another. And because the perpendicular passes through a comma b, we have b is equal to m prime times a plus c prime, which gives c prime as b minus m prime times a. Eliminating all unknowns between these equations, we get d as you see on screen, which is the formula for the perpendicular distance between a point a comma b and the line y is equal to mx plus c. With that said and done, to implement this on our canvas, we are going to measure the distance of each pixel from the line using the coordinates of the pixel as the coordinates of the ideal point. For starters, we shall store that value inside each pixel, and since each pixel color could hold values only up to 255, any distance value over that shall be trimmed to 255. So let us modify our previous program which we wrote to generate lines. This is the part which renders the line, and I shall delete all of that to write our new code. I'll introduce a second for loop inside the first one so that the first loop loops over y coordinates and the second one loops over x coordinates. Inside the second loop, we shall calculate the distance of the current pixel from the line considering the bottom left corner of the pixel as its coordinate. Like I mentioned a second ago, we may have to attenuate the value if it crosses 255, which is the maximum value that a byte can hold. Finally, we can write this value into the three color channels of the pixel, and don't forget to make the pixel opaque by setting the alpha properly. With that, let us compile and run the program, and it looks like the program is generating multiple lines. Oh, uh, so last time we wrote the program so that it generates multiple lines starting from nail 7. So I'm gonna remove the outer loop which did that, so we could render just one line at the moment. Let us compile and run the program, and here is the result. As you can see, this doesn't look anything like a line, but if you think about it for a second, we have actually solved the problem of jaggedness. In this method, pixels away from the line appear progressively less darker, and therefore it appears that the edge of the line is smooth. Let us improve this model and make it look like a nice little thread. An object of a certain color, when looked at from a distance, usually looks lighter than the original color because of optical phenomena like diffraction, refraction, and whatnot. It is not until we get really close to it that we would be able to make out the exact shade of its color. Therefore, a black thread that is strung on a white board appears to have a lighter shade when looked at from even an arm's distance. This is more true if the thread is very thin. Therefore, we have to factor this observation into our model. Second, when you look at a thread up close, it looks like it has a solid core and a thin fray around its periphery. This could be modeled as pixels having a constant darkness for about 2 units around the line, and then the intensity quickly tapering off to white in maybe 1 or 2 pixels. What you see in this graph is just that. The x-axis measures the distance of any pixel from a given line, and the y-axis gives the measure of darkness of that pixel. We start off with a darkness intensity of 150 for pixels that are up to 1 unit of length on either side of the line, then tapering off to 255, which is essentially white or unshaded over the course of another unit of length. Any pixel over a distance of 2 units just stays unshaded. Let us go back to our program and record the three parameters: core width, fray width, and the coarse shade intensity which we saw in our graph. Since we have already calculated the distance, all we have to do is run it through our thread model formula and we should be good. Compiling and running our program, we have the rendering of the thread, and it appears to be a far more reasonable representation than the initial one where we were counting pixels along the x-axis. I think we could still make some improvements by tuning the three parameters we saw earlier. For starters, we could make the thread thinner and lighter, but we shall worry about that later. But what we have to understand is that the underlying mathematical model for the thread shall not change for the rest of this algorithm because we have all we need to fine-tune the rendering of the thread. Now that we have a thorough understanding of how to render a single physical thread on a digital computer image realistically, we shall look at the next natural step, which is to enlist all strings that could be drawn by selecting any two nails out of the n nails on the canvas. The combination formula, which gives the number of ways r things could be chosen from n things, order notwithstanding, says that there are n factorial over n minus r factorial times r factorial ways of doing so. So to choose two nails from a set of n nails, we could do so in n factorial over n minus 2 factorial times 2 factorial ways, which ends up being n times n minus 1 over 2. While this gives the formula to count the number of strings, it does not tell us what those strings are, which is necessary for what we are doing. So let us find another way which solves this problem. Imagine we have three nails on the canvas. We could draw two strings from the first nail to the other two nails. For the second nail, we could only draw one string that goes to the third nail. So for three nails, we could draw a total of three strings between them. Similarly, for four nails on the canvas, we could string 3 plus 2 plus 1 strings for a total of 6 strings. For five nails, it is 4 plus 3 plus 2 plus 1 or 10 strings in total. I suppose you could see the pattern here. For n nails, we would have n minus 1 plus n minus 2 all the way till 1 strings between them. This sum works out to be n times n minus 1 over 2. With this technique, we not only derive the number of strings, but also what they are. We would not be using this as a part of our algorithm, but regardless, I thought it is a nice thing to know. Now let us write a program to implement what we have learned here so far by drawing all possible strings on the canvas to see how it looks. Remember that this is not a part of the algorithm, so let us do it real quick. Before we write the code to generate the strings, let us tidy up the program a little bit. Because we would only be working with shades of gray color, the value of which is the same across the three color channels, we do not have to duplicate those values thrice per pixel. Also, we already know the value of alpha to be 255 on each pixel, and therefore, I'm going to allocate just 1 byte of memory per pixel that stores the grayscale value in it. Since we are not using the image data anyway, I'm going to remove this part which reads the image pixels into the memory. We would also be setting the pixel value during the line rendering phase, so I will just remove this part which generates a white canvas. While writing back to the file, we could simply loop over our pixel array and repeat the value of the color thrice and set the alpha as 255 for each pixel. Oh, and also let us not forget to remove duplicates inside our line rendering loop. Let us quickly compile and run the program to make sure we did not break anything, and it looks like we are good. The next thing I would like to do is take the part of this program which generates the line, which is right here from line 36 to 87, and put it into a separate function which we could then call to generate any line we want. So I am going to cut these lines and put them into a separate function. Right now the nail numbers and nail count are hard coded. So I'm going to delete those and pass them as parameters to the function along with the pixel array and the image width. Let's also add some comments describing the function and also the function prototype. I'll call this function inside the main after allocating the pixel array to draw a thread from nail 0 to nail 9 this time. So let us compile and run this program, and yeah, that looks about right. Let us try that again from nail 13 to nail 33 this time, and yeah, that looks good too. So I think our function is working as intended. So with this, we can go ahead and draw all strings that could be drawn on the canvas with 50 nails. We can achieve that by simply wrapping this function inside two loops, the outer one looping over the first nail, which goes from 0 to n minus 2, and the inner loop for the second nail, which goes from the first nail plus 1 till n minus 1, as we saw a while ago. Let us compile and run the program, and we are seeing only one line, and why is that? What is happening here is that the pixel array is being rewritten inside the loop each time a new thread is rendered. Therefore, we only see the last thread on the picture when we check the result. The solution to this is to allocate another pixel array which would copy and save each thread after it is generated. Once a thread is generated inside the second loop, we shall save it inside our accumulation array with the help of another function which takes the pixel array and the accumulation array as its inputs. So what should we expect it to do? We have two arrays at hand, the pixel array which has a single thread in it at a time and the accumulation array which starts out empty. For the first thread, we just add the color value of corresponding pixels from the pixel array to the accumulation array. For the second thread, we do the same again, but notice how the pixel where the two threads intersect appears darker. We repeat the same for the third thread and so on, and every time pixels get progressively darker as more threads pass through them. To work out the math behind this, let us take one pixel each from both arrays as an example. The pixel on the accumulation array has a value of 150 and the one from the pixel array has a value of 230. So the pixel from the accumulation array is 105 points away from being absolute white, and similarly the one from the pixel array is just 25 points away from absolute white. Therefore, when I add the value from pixel array to the accumulation array, the resulting pixel is gonna be 130 points away from being absolute white, which is 125 points on the color intensity scale. So you are taking the measure of how far away the color of the two pixels is away from being totally white and summing them up to get a measure which tells you how far the resulting pixel's color is away from being totally white. If this measure is greater than or equal to 255, then obviously the result is absolute black. This is exactly what we are going to do inside our copy function. We loop over all pixels and add the value from the source array to the destination like I talked about. Let's add comments to describe what the function does and make sure we write to the file from the accumulation array instead of the pixel array. And also don't forget to free the memory afterwards. Let us try this program on 30 nails instead of 50 for now and see how it goes. And I can't really tell if everything went right or everything just went wrong. So, so, so let's go back and try this with 20 nails and see if it is any better. It looks like we got it right. At least that is what I think. Yeah, yeah, that looks good. Looks like everything worked. Let's do a sanity check. I'm gonna add a thread counter to count all threads we are gonna render and have it printed on screen each time a thread is generated, so we know if we are missing any. I'm gonna disable our previous sanity check message so it would not clutter the console. Let me compile the program and run it. We have 190 threads in total for 20 nails, and that is correct because if you plug 20 into our formula, you would end up with 190 for 20 nails. So, so let's do the same for 30 nails and check the result. And we have a 435 here, which is correct again. So our program is indeed working really well. With this, we are almost done, but for a few rough edges. First, we do not need those threads outside that circular area of the canvas, so let us fix that. Any pixel that is at a distance greater than the radius of the circle should be unshaded. Using Pythagoras theorem, we calculate the distance between a pixel, say a comma b, and the center of the circle as you can see. We just need those pixels beyond the radius to remain unshaded. In our program, I'm going to introduce a new function that does this. It shall take the pixel array and the image width as parameters. We will have two loops for x and y axis, and inside, if a pixel is beyond the radius, we shall make it white. I am using squares instead of square roots here because square roots are expensive to compute compared to just squaring. Let's also run the thread accumulation array through the clipping function. So let's compile and run the program and look at that. That's what we want. So that's one less loose end. The next issue we have is that these threads are a little bit too thick and too dark. I found that setting the core thickness of the thread to 0.5, the fray thickness to be 0.5 times the core thickness, and the core color to 200 mitigates this to a good extent. So let's see how that looks. This is what we get by running the program with these new parameters. And I think we should agree that the new one looks way better than before. So let us call this an improvement. With that said, I think we have everything we need to get into the meat potato of this series, which is making the string art itself. Before we end this, let us quickly recap what we did. We took the pixel counting method of rendering the image of a thread and refined it by using this distance method, with which we were able to generate pretty decent rendering of threads. So in the next video, or starting from next video, we shall look into how we can use what we have learned so far to generate photorealistic string portraits. As always, the code we wrote in this video is in GitHub, the link to which is in the description.